So the final example will show how we may apply this thing to economics. Of course, this is a toy example, but still. A company manufactures two products for $1 worth of product, let's say B. The company spends 45 cents on materials. 0.45. Okay, let me change cells. Then there is labor, and the company spends 25 cents, and overhead it spends 15. And this is product B. Okay, product C, the spending correspondingly, okay, same amounts, 0.4, 0.3, and 0.15. If we have this kind of vector, how can we define this vector in terms of economics? And in terms of economics, it will represent the costs per dollar of income for the two products, B and C. This is each vector. This is the cost per dollar of income. Okay, so two questions. The first one, what economic interpretation can be given to vector, let's say, 100b? Economic interpretation. Vector B is this one, 3 elements. And the second question, suppose the company wishes to manufacture X $1 worth of product B and X $2 worth of product C. Give a vector that describes the costs. Give a vector describing the cost. X1B, X2C. Something like that. Describing the cost, of course, of the company for materials, for labor, for overhead. So the first question, economic interpretation of vector 100b. First of all, we need to produce this vector, of course. It will be 100 times these values. So 100b will be 45, 25, and 15. And the vector 100b lists the various costs for producing what? Again, no math, this is in terms of economic. If the initial vector cost per $1 of income, so this will be the cost per $100 of income. And various costs of producing material, labor, and overhead per $100 of income. That's it. This is the economic interpretation. And the second one, the cost of manufacturing these values is just this answer. It is inside this question. X1B and plus X2C. And again, we are able to form the matrix and try to interpret this matrix somehow. So generally in economy we're asking about different values, dollar values of some number of costs or other values, and we need to somehow interpret it, to give explanation or give economic interpretation. This is pretty very much easy, as you can see in this example. All right. So any questions about this and the previous material? If no, then let's continue to a matrix notation. Okay, let me check. Yeah, recording is producing. All right, matrix notation. So we have the fundamental idea in linear algebra is to view a linear combination of vectors as the product of a matrix and a vector. And here's the definition which permits us to rephrase some of the concepts of our previous hour about vectors in two ways. So first of all, A is m times n matrix with columns a1, an out of course this will be Rn, out of Rn. Then the product will be Ax is a linear combination of columns and corresponding entries. So this is a linear combination when we multiply the columns placed over here in a row and the vectors. Okay. What do we mean here? Let again produce an example for matrix. Let's say there is the matrix -5 and -1 and 3. So this kind of matrix, and our x values, this column is placed over here to the right, 4, 3, and 7. So this is the column, and this is our matrix. We can rephrase the definition given as matrix times axis as a linear combination. So how we will write this? We'll take the first x1 and we multiply it on the first column. So there will be the multiplication. Okay, let me put it this way. So x1 times column plus there will be x3 x2 which is equals to 3 times column, and here will be 2 and here will be -5, and again plus, and the last element 7 times the last column, 7 and -1 and 3. Okay, let me make it a little bit cleaner with 4 and cells number like this. Okay, so we just placed the initial values of vector 4, 3, and 7 over here and multiplied by columns. Okay, and now we calculate the product. So 4 times 1, 0, this will be 4 and 0, obviously. 3 times 2 and -5, there will be 6 and -15. And the last one, 7 times -3 and -1 and 3, this will give us -7 and 21. And we add all these things. So 4 plus 6 plus -7, 0 plus -15 plus 21. So first row in summation will give us 3, and the second row will give us 6. So this is our initial expansion. This is our results of multiplication, and the final result is the summation. All right. Well, to be clear, let's produce another example. Again, we have some matrix and we have some column. So the matrix will have 3 elements by column, minus 3, 0, 2. And the vector will be for 2 elements. So this is our matrix, this is our vector. So first we need to write it down like this. So first element of vector times first column plus second element of vector plus second column. Before multiplication and add. So we're starting out again with 4. Here will be 2, 8 minus 5 plus 7, and here will be minus 3, 0, 2. So this value will produce 8, 32 minus 20. These values will produce us minus 21, 0, 14. We add and have the final answer like this. Okay? Alright, I think it's pretty clear over here. So another example for v1, v2, v3 in this dimensional Rm, write the linear combination of 3v1 minus 5v2 plus 7v3 as a matrix times a vector. So here we have these values, v1, v2, v3. Here is our combination for weights, and we perform this, we produce this matrix. So this is our initial prerequisite. This is the end. This is the final answer. Okay. So let's say that we are having the system of linear equations and we need to produce a matrix. The system of linear equations might be this one. x1 plus 2x2 minus x3 equals 4, and the second equation minus 5x2 plus 3x3 equals 1. So what we should do, we need to write a system of linear equations as a vector equation. So this is like the plain system, and we write it as a vector equation. How will we do that? x1 is the first coefficient, and we search for this coefficient in our first column. And obviously we have x1 only in the first equation, we don't have any x1 in the second equation, so our vector will be 1 and 0 for the first equation and for the second equation. Then plus x2, and we search again. Here we see 2 and here we see minus 5, so it will be 2 and minus 5. For x3, here is minus 1 and here is plus 3. Plus x3 minus 1, 3. And don't forget about the right hand side. This equals to 4 and 1. Let me move this thing a little bit to the left. So this system of equations is equivalent to this kind of notation: x1 times, in square bracket, the vector plus x2 times square bracket vector, and so on. Now we can produce the linear combination. So this squared notation, this squared notation can be rewritten. We see that there are three vectors, three column vectors, and we can form them together inside the matrix. Okay, let's form the matrix. First, second, third, and fourth will be separated with x1, x2, x3. So this is the matrix. This is our vector equal to 1. This is our matrix. This is A. And we need to produce A times X. So the production will be the resulting for 1. So the notation should be kept in your textbooks like this. In your notes, please also keep this kind of notation. It's quite hard to make it look like this in Excel. So what have we wrote here? A times X equals B. So we just performed the matrix notation. AX equals B. So this is the this is what this matrix equation AX equals B is about. From the system of equations, we searched for each column of x's. x1, x2, x3, separated them, formed this vectorized equation. And then we shrink together all the columns inside the whole matrix and name this matrix as A. We leave this x1, x2, and x3 separately as the vector x, and the right hand side as B. So this is our notation. Why is this result important? Here's the theorem. So this is our result, okay, for this example. And this result, the matrix equation, is important. We have the theorem. If A is M times N matrix with columns A1, AN, and if B is Rm version. So keep in mind that m here and number of rows should be the same. Then the matrix equation AXB has the same solution set as the vector equation. So in order to solve this matrix, we just need to produce the linear combination of x times A, x times column, x plus x times column, and so on, equal to right hand side, and this will be the solution for our matrix equation. So these are two forms of notations are equivalent, and Ax equals B will have solution only if there is a linear combination of columns of A. Okay? So remember what we have done in the previous hour. We proved that if B is a solution, then everything is okay. So now we just need to understand if B is a solution for linear combination. B will be the solution if we can form this linear combination. That means all our x's are defined. Okay. So this theorem provides a powerful tool for gaining insight into problems in linear algebra, because a system of linear equations may now be viewed from three different and equivalent ways. We have just demonstrated these three ways in our example. So the first way to demonstrate this is a system of equation, or matrix equation, as it will be right here, and the vector equation, this one, the vector equation. So three different ways for notation. Whether we construct a mathematical model of a problem in real life, we may use any of these notations and perform the computations accordingly. Okay? Generally, all the systems of equation will be transformed to the matrix form, and matrix form, we know how to solve matrix forms. We have done that in our lecture 1, and we are doing this now. Now the important property out of this theorem 3 is the existence of solution. And the existence of solutions forms another theorem. For a particular these four statements, A, B, C, and D, they are all true statements or they are all false statements. Okay? So for each B, the equation has a solution. Each B inside this space as a linear combinations of columns. The columns of A span. A has a pivot position in every row. So it might be not very obvious, but still, theorem 4 is one of the most useful theorems, maybe today, but still. Statements A, B, and C, they are equivalent statements because of the definition of AX and what it means for a set of vectors to span Rm. And actually we suggest that A and D are also equivalent. We can actually provide a proof, but I don't think that this is necessary for economics course. All right. Let's provide another example. We have the matrix A, which is 1, 3, 4, minus 4, 2, minus 6, minus 3, minus 2, minus 7. And we have B, the right hand side, B1, B2, B3. And the question might be raised like this: is the equation Ax equals B consistent? for all possible B1, B2, B3. By the way, those sounds were the modem connected to the internet using the telephone line. This is like the combination of different pitched tones in order for connection to be established. The maximum speed was 56 kilobits per second. Very happy childhood for many of teachers in our department. Okay, so is the equation ax times b, so this is b, actually x is not given but it is assumed that this is x1, column for x1, column for x2, and column for x3. Consistent for all possible b1, b2, b3. What should we do? We start again with our matrix. We first form the augmented matrix. Okay, let me number and b1, b2, b3. So this is the augmented matrix, and again we're starting with the first column, first row, produce zeros here, and so on. So our sets of equivalent transformations will give us 1, 3, 4 b1 stands. Here we write 0, 14, 10, and here we write b2 plus 4 b1, 0, 7, 5, and here we write b3 plus 3 b1. Okay, so this is the first equivalent transformation, and the second equivalent transformation we use this pivot element, produce zeros over here. So it is obvious that second row is twice the third row. So we can just transform it to zeros. Let me do it lower. So here is 0, here is 0, and b3 will be minus 0.5 sum of b2 and 4 b1. Don't forget about this extra column about b. So what should we see here? That the third entry in column 4, this one, b1 minus b1 minus, can we extract something? b3, 3b1 minus 5b2 plus 2b1. That means b1 minus, that actually transforms as b1 minus 0.5 b2 plus b3. Okay. What can we say about the consistency of a quotient? Consistent, that means it has the solution. Now we don't have any solution. The system is not consistent because some choices of b will form these values to be non-zero. Okay. The matrix, the equation ax equals b is not consistent for every b. Some choices of b can make this thing non-zero. So this is the result, the answer for our task. When the system will be consistent? Only if this value b1 minus 0.5 b2 plus b3 equals to 0. And if we try to produce this equation and equalize it to 0, what can we see in like geometric interpretation? What can we see? We have three values, b1, b2, b3. That means there is a three-dimensional space, and inside this three-dimensional space we have some kind of a plane, and this is the span inside the plane. Plus b3 equals to 0. So this equals to 0 means span through the origin. And if we have something like this inside, we might encounter something like this, which comes through the origin, and this is the span for our spaces in three-dimensional space. The coordinates b1, b2, b3. Something like that. Again, you can produce the graph in some graphical software and look, maybe it will be actually inverted a little bit. I think it will be more inverted like this. It goes from the origin. Okay. What is this example about? This example is about computation of AX. Two x1 plus 3x2 plus 4x3 minus 3. Yeah, of course, from the definition, there will be some tasks about first reproduce this matrix in the vector form, and for the vector form you just place x1 times first column plus x2 times this column plus x3 times this column. Then you combine the x1, x2 and x3 inside. So let's say x1 times the column 2 minus 1, 6 plus others. This is the first option. The second option, before you get to this final solution, you multiply 2x1 minus x1 plus x1, and you form the summation of these three vectors, and the third step will produce this kind of matrix. So if you are asked to compute, and please write like the vector form and include the vector form in the computation, that just means these simple steps. Yes. Okay. So what we have, computation theorem, I think there should be something more, but okay. Let's look at the properties of the matrix to vector product AX. So here we produced, right? Yeah, we need a couple of extra examples before we go to theorem 5. The first example involves row vector rule for computing AX. So if the product AX is defined, then the ith entry in AX is the sum of products of corresponding entries from row I of X, I small, come on, I need small. Okay, this one is small, I don't know, it always changes, of I of A, and from vector X. So this kind of rule, I explicitly wrote it for you, but actually you'll memorize it as a rule for computing matrices, because you'll do it like maybe 100 times and everything will be performed automatically. So let's apply this rule to matrix and vector. The matrix will be 1, 2, minus 1, 0, minus 5, and 3, and the vector will be 4, 3, and 7. So how can we apply this rule? How we produce the product for matrix? This is matrix A, this is vector X. We need to compute A times X. So we will, I will write for the first time for you, this will be 1 times 4 plus 2 times 3 plus minus 1 times 7. And this will be our first element. And the second element will be 0 times 4 plus minus 5 times 3 plus 3 times 7. So obviously 1 times 4 plus 2 times 3 plus minus 1 times 7, this is forms the single value in the result when we compute this. And the second value will be 0 times 4 plus minus 5 times 3 plus 3 times 7. Okay. So this value after computation will form just one scalar 3, and this computation will form scalar which is 6. And as a result, AX equals 3 and 6. Okay. The result of this multiplication will be just as here we had this value, we multiply it, produce the multiplication, and here's the result. Just a column vector. Over here is also just a column vector, two values. Please compute 28 minus 5, let's say minus 302, and vector is 47. Matrix and vector. Check your result. Minus 13, 32, and minus 6. Very often you will encounter with problems where the matrix is in the diagonal form. What does it mean? That means only diagonal elements are non-zero elements and the other elements are zeros. To be perfectly clear, the diagonal matrix, let's say like this. This is the diagonal matrix, and suppose you need to find the product AX where X is RST. So what will be the result for here? So obviously you don't need to perform these summations, these are redundant, because any zero elements times other will be zeros. So we perform only multiplication 1 times R, 1 times S, 1 times T. So the result will be equal to RST. Okay, just pay attention on the contents of your matrix. If there's diagonal matrix, just perform the single multiplication. Actually, this type of matrix might be referred as I. Here I is capital, and I generally refers as identity matrix. So IX equals this. And as a general rule for identity matrix, IX equals X always. Alright. What will be the time? Okay, I think that's enough for now. Please have a break.